In question 1, we're given the Venn diagram here where P is a probability showing 3 events A, B, and C with the associated probabilities. And in part A, we need to find the value of P. Well, we know that the sum of the probabilities here should give a result of 1, which means we're looking at 0.2 plus 0.2 plus 0.1 plus 0.2 plus P being equal to 1. This gives me 0.7 plus P being equal to 1, and therefore P is equal to 0.3. In part B, we need to write down a pair of mutually exclusive events from A, B, and C. Now, mutually exclusive events are those that have an empty intersection. So looking at the Venn diagram here, we can see that A and C have no common region, and therefore the answer to part B would be A and C. In question 2, we're given a partially completed table and a partially completed histogram giving information about the ages of passengers on an airline. We've got no passengers aged 90 or over. This is the frequency table here. Some of the information, the frequencies for these two classes is missing. And then we've got the frequency density against the age here. It's the histogram. And we've got the bar between 0 and 5 missing and the bar between 20 and 40 also missing. And we need to complete the histogram. Well, let's start by reminding ourselves that in a histogram, the frequency density is given by the frequency over the class width. And I will try and construct a frequency table based on the information provided in the frequency table and the histogram here. So let's see, we've got the age in years, we've got frequency, class width, and frequency density. Now we can see from the frequency table that the classes are 0 to 5, 5 to 20, and so on. So let's start with the class width. For 0 to 5, the class width is simply 5. Then we've got a width of 15. Then it's 20, 25, 15, and 10. I will fill in some of the frequencies provided here. So from the frequency table, we've got the first 3 frequencies and the last frequency. So in the table, I'm writing here 5, 45, 90, and at the end, I've got 1. So if I do frequency over class width, I'm finding the frequency density. So 5 divided by 5 is 1. Then 45 over 15 is 3. 90 over 20 is 4.5. And finally, 1 over 10 is 0.1. This will help me scale the vertical axis, the frequency density axis, because I know, for example, that in this class here between 5 and 20, the frequency density is 3, which means I can put a 3 here. This is a 2, this is a 1. I can go up, this is a 4, and this is a 5. And I can read off the frequency densities for these two classes here. It's 5.2 and 4. So let me fill in the table here. It's 5.2 and then 4, which means I can go back here and fill in the frequency by doing class width times the frequency density. So if I do 25 times 5.2, I get an answer of 130. And then if I do 15 times 4, I get an answer of 60. So I have the completed frequency table, and I can go to the histogram here to fill in the 2 bars missing. So for 0 to 5, we found the frequency density of 1, so the bar will look something like this. Whereas for 20 to 40, we found a frequency density of 4.5. So this completes the histogram for 3 marks in part A. In part B, we're asked to use linear interpolation to estimate the median age. So let's recall the frequencies we found in part A. I will add an extra column of cumulative frequencies, which is a running total as we go from the very top to the bottom here. So I start with 5, then 5 plus 45 is 50, plus 90 is 140, plus 130 is 270, plus 60 is 330, plus 1 is 331, which is the total number of observations. Now we're looking for the median here, so I'm going to do n over 2, where n is the number of observations. So it's 331 divided by 2, which gives an answer of 165.5. So I'm trying to interpolate for the 165.5 position. We can see that the first 140 observations were up to 40. So the 165.5 observation would be between 40 and 65. So I quickly draw this diagram here. We're looking at somewhere between 40 and 65. We're looking for the median, which I will call M. Below, I'm putting the frequencies. So we had 140 observations up to 40. We had 270 observations up to 65. And we're trying to interpolate for 165.5. So I'm using a ratio here. The small gap over the small gap is equal to the big gap here over the big gap. This leads to M minus 40 over the 165.5 minus the 140 being equal to 65 minus 40 over the 270 minus the 140. This leads to M minus 40 over 25.5 is equal to 5 over 26. Well, if I cross multiply, I get that M minus 40 is equal to 4.9038, and therefore the median M turns out to be 44.9, correct to 3 significant figures. We are then told that an outlier is defined as a value greater than the upper quartile Q3 plus 1.5 times the interquartile range. We are given the lower quartile Q1 and the upper quartile Q3, and we need to determine, giving a reason, whether or not the oldest passenger could be considered as an outlier. Now remember, we were told in the question that there was no passenger more than 90 years in age. So let's start by calculating the interquartile range, which is defined to be Q3 minus Q1. This is 58.9 minus 27.3, which gives an answer of 31.6. And then let's calculate the limit beyond which outliers are to be found. So we'll be calculating Q3 plus 1.5 times the interquartile range, which is 58.9 plus 1.5 times the 31.6, which gives an answer of 106.3, which is greater than 90. And therefore we conclude that the oldest passenger cannot be considered as an outlier, because remember, the oldest passenger was up to the age of 90. Anything above 106.3 would be an outlier, but we have no observations beyond 106.3. In question 3, we've got Helen, who is studying one of the qualitative variables from the large dataset for Heathrow from 2015. Now, qualitative variables are those that are not measured on a meaningful numerical scale, so they do not attain numerical values. Now, she started with the data from the 3rd of May and then took every 10th reading. There were only 3 different outcomes with the following frequencies. So outcome A appeared 16 times, B appeared 2 times, and C only appeared once. And we need to state the sampling technique Helen used. Now, since she was taking every 10th reading, she was working in a systematic way. So she began on the 3rd of May, then it was the 13th, the 23rd, and so on. And this is called systematic sampling. In part B, we need to use our knowledge of the large dataset to suggest which variable is being studied, and we need to state the name of outcome A. Well, we don't have a lot of qualitative variables in the large dataset. One such variable is the daily mean wind speed, the Beaufort conversion, which happens to be the variable being studied here because it is heavily dominated by the outcome light. As we can see here, outcome A appeared 16 out of the 19 times in total. So we're looking at the daily mean wind speed with A being associated with light. Now, George is also studying the same variable from the large dataset for Heathrow from 2015. Now, he started on the 5th of May, taking every 10th reading, obtaining the following results. As we can see again here, the sample is heavily dominated by outcome A. Now, Helen and George decided they should examine all of the data for this variable for Heathrow from 2015, obtaining the following outcomes. Again, A appearing 150 times, which is a lot more than B and C. And we need to state what inference Helen and George could reliably make from their original samples about the outcomes of this variable at Heathrow for the period covered by the large dataset in 2015, we certainly see the same conclusion arising from both samples, and that is that variable A occurs most of the time. In question 4, a nursery has a sack containing a large number of colored beads, of which 14% are colored red. Aliyah takes a random sample of 18 beads from the sack to make a bracelet, and we need to state a suitable binomial distribution to model the number of red beads in this bracelet. I will start by defining my random variable x to be the number of red beads. Now, each bead selected could be red or not, so we're looking at the binomial distribution. We've got 18 beads to be selected, so n is 18, and the probability of success is 0.14. In part B, we need to use this binomial distribution to find the probability that Aliyah has just one red bead, or that we've got at least 4 red beads. So for the first part, we're looking for the probability of x being equal to 1. So I'm going to go on my calculator, I press menu, option 7, it's option 4 binomial PD, and then option 2 variable. My x is 1, my n is 18, and my p is 0.14. I get an answer of 0.1940. And then for I, we're looking for the probability of x being greater than or equal to 4, which is 1 minus the probability of x being less than or equal to 3. Remember, the calculator can give you cumulative probabilities, which means we need to be looking in the less than or equal to direction. So I press menu again, option 7, I scroll down, option 1 binomial CD, I choose 2 variable, my x is 3, my n is 18, my p 0.14. I get an answer of 0.7618. So we're looking at 1 minus 0.7618, which gives me an answer of 0.2382. In part C, we need to comment on the suitability of a binomial distribution to model this situation. Now, we were told in the question that the sack contains a large number of colored beads. This is crucial here because we can say that since the sack contains a large number of beads, the probability of picking a red is relatively constant at p 0.14. So as we remove beads, the probability of choosing a red one does not change significantly, and hence the binomial distribution is suitable. Now, after several children have used beads from the sack, the nursery teacher decides to test whether or not the proportion of red beads in the sack has changed. Now, she took a random sample of 75 beads, finding 4 of them to be red, and we need to state our hypothesis clearly and use a 5% level of significance to carry out a suitable test for the teacher. Well, we know that the random variable x here follows a binomial distribution with parameter n being 75 and probability of success being p. We know that the initial hypothesis, the null hypothesis, says that p is 0.14, and the teacher here is looking for a change in the proportion of red beads. So this is a two-tailed test. The alternative hypothesis says that p is not equal to 0.14, and we're working at the 5% level of significance. Now, assuming that the null hypothesis is true, so under H0, we've got x following binomial with n being 75 and p being 0.14, and I will be investigating both directions because this is a two-tailed test. So I will start with the probability of x being less than or equal to 4. So I'm going to go on my calculator, I press menu, 7, we go down, option 1 binomial CD, option 2 variable, my x is 4, my n is 75, and my p is 0.14. This gives an answer of 0.0151, and I could also investigate the other direction, so the probability of x being greater than or equal to 4, which is 1 minus the probability of x less than or equal to 3. So let me go on my calculator, I press 3 here, I do the calculation, it's 1 minus 0.00462, which gives an answer of 0.99538. Now, I need to compare these probabilities not against alpha, but half of alpha, because it is a two-tailed test. So I'm halving the significance level, and we can see that this here is a very small probability. It is actually less than 0.025, which is exactly half of the significance level, which means that we're looking at a significant result. We reject H naught. We need to put a conclusion in context here. We've got evidence that the proportion of red bits has changed. In part E, we are asked to find the p-value in this case, and the p-value is defined to be the probability we found in the extreme tail, so the 0.0151 times 2, because we are looking at a two-tailed test. So the p-value here is equal to the probability of x being less than or equal to 4 multiplied by 2. So this is 0.0151 ... times 2, which gives an answer of 0.0301. In question 5, we've got two bags A and B, each containing balls which are either red, yellow, or green. Now bag A contains 4 red, 3 yellow, and then green balls, while bag B contains 5 red, 3 yellow, and 1 green ball. Now we select a ball at random from A, placing it into B, and then we select at random from B, placing it into A. The probability that bag A now contains an equal number of red, yellow, and green balls is P, and given that P is greater than 0, we need to find the possible values of N and P. Now we really need to get a really good understanding of what's happening here. We are drawing from A into B and then from B into A, and we know that in bag A we had 4 red, 3 yellow, an undefined number N of green balls, while bag B has 5 red, 3 yellow, and 1 green ball. And we need to consider the different scenarios that will lead to bag A at the end of the day having the same number of red, green, and yellow balls. So we can see that one scenario would be to leaving the red balls untouched and then removing a green one and then putting it into bag B and then removing a yellow one from bag B into bag A. So something like this. I choose from bag A, which initially had this setting here. I remove a green one. So bag B now contains 5 red, 3 yellow, and 2 green. And then I remove a yellow one from bag B, so that we end up here with 4 red, 4 yellow, and therefore we must be having 4 green balls as well. And if we think about the process we just applied, we removed one of the green balls here. We never returned a green ball, so it must be the case that for us to end up with 4 green balls, we started with 5 initially. So this means that N is equal to 5, and I can use this to find the associated probability. So it's the probability of choosing a green one from the bag A times the probability of choosing a yellow one from bag B, giving me the answer for P. Now we had N green balls initially, so N over the total of 7 plus N, because we had a total of 7 plus N balls in bag A, times the probability of picking a yellow, which is 3 over 10, being equal to P. Now we have found N to be 5 in this case, so P is equal to 5 over 7 plus 5 times 3 over 10. Now if we do the calculation here, get that P is 1 over 8. So this is one of the possible scenarios. N is 5 and P is 1 over 8. Now an alternative scenario would be to start again from bag A. This is the initial setting. I will remove one of the red balls. So I pick a red ball from bag A. I put it into bag B, which now has 6 red, 3 yellow, 1 green. And then I remove a green one from bag B, ending up with 3 red, 3 yellow, 3 green. Now remember, I removed a green from bag B, putting it back into bag A. So for me to end up with 3 green balls, it means I started here with 2 green balls. So N here is equal to 2. The probability I choose a red one at the beginning is 4 over 7 plus N. The probability of picking a green one from bag B here is simply 1 over 10. So 4 over 7 plus N times 1 over 10 is the value of P. So I'll be using here N is 2. So P is equal to 4 over 7 plus 2 times 1 over 10. If we do this calculation, we get an answer of 2 over 45. So all in all, we've got two cases. N is 5 with P being 1 over 8 in this case, or N is 2 with P being 2 over 45 in this case. Now in these questions, we need to get a good understanding of what's happening. Sometimes choosing a way of illustrating what's happening helps us determine the different scenarios that we need to consider, ending up with these two possibilities.